All right, so we have this problem. This is problem one from your homework. Some strange man, concerned about his weight, decides to put himself on a scale in an elevator. So here's the strange thing. If you're concerned about your weight, I'm going to go in public and let other people be concerned with me. All right, that doesn't make any sense. So the guy has issues. All right. Uh, in this problem, he stands on a scale that's initially moving upward at 3 meters a second, so it's a constant speed. If the acceleration is 0, which is what you have with constant speed, then you would expect while the speed of the elevator is constant, his weight would be a true weight. It's when the acceleration is not constant, then we'll have an apparent weight that's at odds with the true weight that we have if he was motionless or acceleration 0. Now, the nice thing here is that we're given enough information to calculate the acceleration. Whoops. So if you do a velocity time graph, acceleration time graph, what you find is that, well, he's at 3 meters a second, and comes to a stop. And we know that this change in y was 2 meters. So that means 2 meters is going to be equal to 1/2 delta v delta t. All right. Well, we know that since the slope of the velocity graph is a negative slope, that means it's associated with a negative acceleration. So delta v equals a delta t. Well, this also equals a negative 3 meters per second, because that's what the change in speed is. It goes from 3 to 0. 0 minus 3 is negative 3. Okay? So that means I could take this negative 3 meters per second value and replace that up here. So that's going to lead me to two things in this problem. It's going to lead me to the time that it took to decelerate, which means I could go back to the bottom equation and obtain the acceleration value. So I'll use the fact that the change in speed is negative 3 to get the time. Then I can use that time to get acceleration. So ultimately, this will lead you to time equals some value, which means you'll put that time down here and you'll get some value, which I'm not going to do for you. I'm just going to set you up so that you can do for you what you are more than able to do for you. All right. So that's the graphical. Every one of these problems in this homework assignment, you will benefit from using graphical analysis. Could you do it some other way, just equations? Sure, you could. All right. So pick your poison. All right. So we have that, but we also need to model the forces and figure out what's going on here. So here's the man, and he has some true weight, mg. There's some surface reaction force, or the normal force, N, that's going to oppose that. So the trick is which way is the acceleration in this problem? Well, we already know which way it is. It's down, because I did the graphical analysis. So acceleration is negative in this problem. Could you have known that without doing graphical analysis? Sure. You could have said, well, he's going from a speed to 0 speed, that's decelerating, that's downward acceleration. But What's weird is just like when you hit the brakes in your car, you're still moving forward. You're just slowing down as you move forward until you come to a stop. No different. The brakes on the elevator. All right. So that means when we sum our forces, and I'll just leave the y's off because everything is in the y direction. What do we get? We get an up force minus a down force equals a negative ma. It has to be that way. So the normal force here will be mg minus ma, which means I have mass times g minus a. So what we expect to be true, I would expect that as I'm what happens is you kind of can feel it when an elevator's coming to a stop. As you move up, you kind of feel lighter for a second. Okay, it's like the floor, you left the floor a little bit, all right? And so the same, that would show up on a scale. And it makes sense that gravity is going to be this constant that just got a chunk taken out of it due to the acceleration of the object. All right, so this makes sense that I would have an apparent weight less than my true weight because it's going to be the true weight maker of G minus the apparent weight maker of A. And the opposite would be true going down. As it's slowing down, coming to a stop as you move down, the acceleration's up, so it's adding A, increasing your weight. Your apparent weight's larger than your true weight on the opposite trip. All right, so that's the first problem in the homework is that one, which I'll leave you. You're not done with it. You need to figure out what acceleration is. You need to figure out what the scale reading is going to be. So the normal force for problems like this, that's what a weight scale is giving you. The surface reaction force to the weight that's on top of it. So weight scales is catchier, easier to market than normal force meters. All right, not many people stand in line to get a normal force gauge. All right, but the weight gauge, that's going to be equal and opposite. All right. Now, so the problem number 2 with the girl and the rope, as her weight down, there's tension in the rope due to that weight, and then she accelerates upward. So my sum of forces equals ma, so T minus mg equals ma. And you would figure out what the tension in the rope is. I didn't ask you what it was, I'm giving you modeling tools, and you model with it and see what you can generate. All right. And once you know what A is, which is evident in the problem, it's solved. All right. Problem number 3 deals with a couch, a lovely couch that somebody leaves out on the curb. So here's a couch, which I will model with a block. It's a 100-kilogram couch. You move it at constant velocity, meaning change in velocity is 0, which means acceleration is 0. So it's at a speed, but it's a constant speed. All right. So it's a constant acceleration. All right. There's 0 in this case, even though it's moving. And friction coefficient. So we know, so there's going to be an applied force, a big F, and then there's going to be a frictional force, little f. So by the way, the conventional symbols friction will always be a lowercase f. That's just the conventional way of every textbook in the galaxy does it that way. And then the other forces are always a big F if it's some contact force, unless it's tension, which we'll use a big T for, et cetera, et cetera. All right. So in this one, force diagram, you have the weight of the couch, you have the normal force, you have the big force applied, and you have the frictional force like that. And I've drawn it that way. The normal and the mg are equal and opposite, same length, different directions. But since I know it's moving, I know that the applied force has to be bigger than friction. It would have to be at least equal to it. All right. And in this case, it would have to be equal to it when you sum the forces, because if acceleration is 0, okay, we'll do in the x direction, F minus F would equal 0, which means magnitude-wise, they're the same. So I would have to come back here and correct my diagram and make those equal since it's constant speed, meaning 0 acceleration. So that's the interesting thing about friction. You don't actually have to exceed friction to cause motion. You can match the force, and we call that impending motion. It may or may not move at that equal value. So static friction tends to be just a little bit larger, and once you get it moving, it's easier to keep it moving. So that's kinetic friction. Once it's moving, it's kinetic. Before it's moving, it's static. Duh. Okay, that makes sense. Static frictions are always larger than kinetic frictions in a given situation. All right. Now, if I knew that it was a non-zero acceleration, then I would make the force bigger. All right. So, and then of course, this is mu n, and you would get that n equals mg from the force diagram in the y direction, which you would plug into the x equation, and you would compute. You could determine what the applied force is. It's going to be the coefficient times the mass times gravity. That's how much force it's going to take to push this couch to your house. So a 100 kilogram couch, that weighs slightly more, basically what I weigh. I'm like 208. It's 220. 100 kilograms more like 220. So you're pushing your professor down the street. Please put a tarp under me so I don't get any scratches, all right? No. So that's a setup for that problem. Now, number 4, we're told that a boy pulls a 30 kilogram sled, which includes the mass of his kid brother, along ice. I have ice. I have 30 kilogram sled. Now we're told in the rest of this problem, the boy pulls on the tow rope at 60 degrees above the horizontal. So there's a rope. There's going to be some tension in this rope. And we're told the rope is angled at 60 degrees. That looks more like 45, but who cares? All right. And this is a strange family because the older brother knows that his younger brother always cries upon reaching a speed of 2 meters per second. Why anybody would know this about their family? But everybody here is part of a family, and families can be strange. All right, so this family has their quirk, you have yours. Perhaps the kid has his own iPhone with a speedometer on it, and he's always noticed on the ice that the kid screams when it hits 2, who knows? Maybe it's just an innocent, not as weird as it sounds. So it takes the boy 4 seconds to make his brother cry. Well, again, what's the acceleration going to be? 2 over 4. Change in speed is 2. The time that it took to do it was 4. 2 fourths is half a meter per second. So boom, we don't have to do graphical analysis. It pays a couple of these. It pays to do it, and a couple of them, why bother? It's just too easy. All right. And it tells us the frictional coefficient. So here we know that there's friction. There's a friction force there. And mu is given as 0.15. What's that? Oh, sorry. Change the color here. So friction, 0.15. Force diagram time. So we know that there's a mass gravity. Okay, why? Oh. All right, so the weight force would be down, obviously. The normal force would be up. There is a friction force going to the left or opposite of the direction that tension is, but know this. This tension in the rope can be understood as X and Y components. So the resolved tension would be an X component, Y component, if we were to think a rectangular vector. There's a bunch of oomph in the X direction and some more oomph in the Y direction. That's the way we can think of it. All right. And so we have a tension in that way. Now, the thing to realize is that we technically have a Tx and a Ty going on here. So when we sum the Y forces, which are going to be zero, right? Because it's not moving in the Y direction. It's staying level ground. So I know the sum of forces in the Y direction has to be zero. The MA is zero in that case. But I have an interesting thing here. I have the normal force up plus the Y part of the tension in the rope. Those are the up forces. The down force is singular, it's just the weight, and that equals zero. Well, the normal force will end up being the true weight of the object minus this Y component of tension, which I can write as the full force that's applied, which is what I'm going to want to know, times sine of 60. That's a third version of the normal force that we've seen today. We've seen the normal force when it's just mg for straight up and down, no extra forces or motion involved. We've seen mg cosine theta when it's a fraction of the true weight going down an inclined plane. And now we see the normal force. Whoops, that's supposed to be minus. Sorry about that. Make sure you get your minus in there. All right, mg, I'm going to adjust this. I'm going to rewrite it just so that there's a little bit of clarity. mg minus t sine 60. Now because some portion of the pulling was straight up, therefore it's taking away from the true weight. This would be the same as if you were standing on a scale and somebody came and lifted you up a little bit, or had a rope under your arms and pulled you up on a pulley a little bit. It would make your weight look less than it is. All right. So now I have the normal force, and if I do the sum of x forces, which I know are going to be a non-zero acceleration, so I know it's going to be ma in the x direction. Now I have t in the x direction, that's going to the right, which is positive, minus friction, those are the only x forces, will equal, according to Newton's second law, mass times acceleration in the x direction. All right? Well, Tx would be t cosine 60. Friction is mu n, so I'll just leave that ma for now. Well, t cosine 60 minus, well, the mu is 0.15. N is this big ugly thing, mg minus t sine 60. And that has to equal ma. So I sort of ran out of room there. I'm not going to do the whole problem for you, but you need to know something about that. So it's just an algebra problem now to solve for T, tension in the rope. What's the force applied to produce this crying kid brother? Which is mildly entertaining to a point, and then you want to leave him out in the snow. All right, so as long as it's not too cold. The rocket problem. I am going to suggest that you remember the impulse momentum theorem, which is impulse is force times time, and momentum is mass times changing speed. In this rocket problem, you're told what the mass of the rocket is. You're told how much force it produces and how long it produces that force. You should be able to determine the change in speed. However, you would have the weight of the rocket. You would have some force applied to that rocket, which means its acceleration is moving upward. We're also pretending that the mass of the rocket doesn't change during this 15 seconds, which is silly. But this is a pretend problem to get us to do the math. Obviously, the mass of a rocket changes dramatically every second it's in flight. The vast majority of the weight of a rocket is its fuel. And we have to burn a whole bunch of fuel so that we get to escape velocity in a relatively short amount of time. We need to get to like 11 kilometers a second to escape Earth's gravity. So it takes a minute or so to get all that done. But as it's losing mass, if the thrust is constant, it will speed up. Just like if you were going down, if you were moving and you could throw weight out of the cart, you would speed up. As long as you could throw it out in a way that didn't change, exert a force on the cart. So make sure that you can just go straight to that in problem number 4. All right. Now, problems number 6 and 7 in this are fundamentally the same thing. And if you look at number 6, and we'll just stop the recording here.